Hello there, welcome to another video of Primeology. In this video I want to talk about ColT5, faster long-range transformers with conditional computation. This paper is published in 17 March 2023, slightly new, by Google Research. And for understanding that, we need to know what is T5 and what is some of the training paradigm like UL2, Pegasus, and stuff like that I will explain all of them in this video. So it is not related to just this paper. We will walk through some papers, and I have a plan to write some code and see some of the codes from ColT5 implemented by Lucidtrain. And maybe we have like rewrite some of those parts. So basically, let me start from ColT5, and then during explaining that, we need to know T5 and training paradigm. So what is ColT5? So based on the name, you see that this is faster inference or faster training, and we have long range coverage. So faster long range transformer. And how is that with conditional computation? That is a very good abstract of the whole paper. I will talk about that in few minutes. So about the faster part, when we have a very long token, like 64K input length, for example, if we want to apply a very like dense attention and MLP layer, it would be slow um, in many different way. For example, if suppose we have fixed the problem of positional embedding, like using alibi or rotary embedding or anything, still for applying the attention and MLP, we have problem because uh, its complexity increased quadratically. And that's why they have implemented routing mechanism. So if you have 64K input, you route some of those parts, or maybe like 500 of them, to a heavy attention, and the rest or all of them can go to the light attention. And these light and heavy are very similarly implemented, just the number of heads and dimension for the heavy attention is much larger than the light. And by that routing, you pass just the query and the values, uh, some part of that to the heavy attention and just apply heavy attention on those parts. Then you will have another routing on the result for the MLP. Similarly, some a small portion of the whole input go to the heavy MLP and the other part go to the light MLP. And they can also be like sum them together. So you will have light attention, then you will have heavy attention, sum them up, have another routing, sum them up, and you will have the result. And the reason is that so you will apply less computation on the long input. So that was the reason it is faster. And the reason it is long range is because of that routing. So if you have like 64K and we have uh, question answering, in many cases, we don't need to put attention on the whole text. It's very rare that we want to like do summarization or something that we need to put attention on the whole thing. But like for extracting some entities from that document or for doing question answering stuff like that, we need to put attention on a small portion. And that's why it can some sort of uh, handle long range input tokens. That's the whole idea of ColT5. But there are some part here that we need to discuss. First of all is about the routing. How is routing work? I think this is very important part. And it is not discussed very clear in the paper that how routing exactly is working. As we will reach the code, we will see some of the problem that we will face. And overall, it is good implemented by Lucidtrain. Another part we want to talk about is the training paradigm. And let's go down. So I don't want to read the abstract because I already mentioned everything in the on the diagram here. And let's see this like comparing long T5 and cold T5. So long T5 is the generation after T5, and it's try to somehow apply transformer on longer range by applying uh, localization and sampling and making the attention, like making the input token sparse. Like, for example, using average pooling or maximum pooling, stuff like that. Like, for example, you have 64K token per 16 token, you will apply like an average and apply attention on this um, sampled window instead of applying the attention on the whole thing. That is the main concept of LangT5. So for ColT5, we do the same thing for like having the long range, but another difference is one of the difference is ColT5 is trained on the UL2 paradigm, while LangT5 is trained on Pegasus paradigm, and I will talk about them. So let's I think let's just start with this paradigm of training, then we can go to the flops and wrap this up. So for understanding this, we need to know the T5 training. Let me go here and bring the T5 paper. This is the T5 paper in 2020, exploring the limit of transfer learning with a unified text-to-text transformer. So actually the main idea of the paper is we can convert any problem to the text-to-text and sequence-to-sequence modeling, and we can solve that problem. And the reason it's called T5 because we have 5T in this text-to-text transformer. They are mentioning here text-to-text transfer transformer. So we can have like translation, we can have summarization, everything can be just by a sequence-to-sequence modeling. But the main idea, let me go down here. So we know that there are three kind of models. One is the decoder only, encoder only, and encoder decoder. And encoder only is like BERT, that we have tokens from future and past. And for GPT is like decoder only, that we have autoregressive way of predicting next token. And we have encoder decoder like T5. And the way that you train this model for BERT and GPT is okay, because we know that like for GPT you need to have a language modeling or causal language modeling data set. You can use that recursive way. Or for BERT you can use like mass language modeling. You mask some of the word, corrupt them, and we try to fix them. But for T5, they are different paradigm to train them. Let me go down here. So for T5, if you have this kind of fully visibility over the context, yeah, like these are the inputs and these are the outputs. So if you get the first input, you will predict the first output. If you get two first input, you can predict the next one. This is the causal language model. For full visibility, it's like BERT. You mask one of these and you say predict this one. And there is another way, it's causal with prefix. So it's like combination of BERT and language modeling causality. So it's like we can have some prefix of the text. For example, the math is sat, and then we want to predict the next part using autorecursive. So uh, we have some information from the past, but that information is not only one token, it starts from pre-context. That's why it's called prefix. That is uh, like one way of looking to the training uh, uh, decoder only model, I can say, or encoder only model, this one. You can see one of the example like prefix, we have connection on this part of the model for two direction, for bidirection, and for another part is like just language modeling. So I just want to walk through this very fast because our main concept is about our main objective is called T5, but we need to know T5. So they're talking here about training paradigm. So you want to train T5, you have a sequence to sequence modeling, but how you want to train it? You want to train it using mass language modeling, you want to train it using just language modeling autoregressive way, or you want to do something else. So they have three paradigm here. One is language modeling, one is BERT style, and one is deshuffling. And we know these two. We talked about it now. A deshuffling means that just shuffle the words and try to predict the correct order of the words. That's one task. For birth style, we can do different things. One is just to mask that specific word, or we can replace that span. It cannot be just one word, it can be like two, three token. We will talk about that in a few minutes. But you can replace it instead of just putting a masked token, just bracket M, um, open and close. You can put another token that is not relevant to that context and let model to fix that. Or you can drop that token completely. Like you have a sentence, a cat sat on mat. You can remove the cat. So you can just say a sat on mat. And the model should predict the cat in between. So that is the three different things that we can apply for the birth style. And for these two, it is okay. But for these birth style, we can also have different corruption rate, like how many of the words or how is the frequency of that corruption. And then we need to know how many tokens need to be corrupted. Like is it 10 token, 5 token? So they're showing here that we need to have a larger range of corruption and not very long corrupted span lengths. Like 10 is not getting good result, but like 2, 3, 5 is not very different. But like 50%, 2, 3, 5, and all of these paradigms. So the model T5 is trained on this. But there is still one problem here. So let me go back here. Okay. So the GPT is like not bad in few shot paradigm, but it is not good in fine tuning. Like if you want to fine tune it in a specific task because it is autoregressive way, the performance is not good as when we apply uh, the, the T5 training. So if you fine tune T5, its performance is really better than like GPT models. I think there are some tables here. They have lots of ablation study like why they have done that. And I think they have a comparison. I think they have. I'm not sure about it, but they have shown that their model is very good in fine tuning, but it is not good in few shot and one shot learning. So that's why a new paradigm ULV2 is uh, worked by the Google Brain. And let me go back here. I'm just thinking about, yeah, so I think that was a different team. Yeah. So they talked about UL2, and UL2 said that, okay, you are training this, you're training T5 on a different paradigm that we discussed, but still the performance is not good for the few shot or one shot. That's why they have mixture of denoiser, and this is different than mixture of expert. The mixture of denoiser paradigm for training means that you can have a token X, so bracket open, bracket close, and inside there is X or R or S, and you can decide that like what is the kind of data. So instead of like training just one model with just one mask or replacing or stuff like that, you will have some specified token. Like in inference time, when I know that the like uh, a very long sequence of the input is corrupted, so I can say that bracket S. So it's like sequential denoising. So the model somehow gets some hint about how it's gonna think about that problem. Is it a short span and the number of corruption was low, or the number of corruption was high and it was short span, or it was extreme noise on the text. So you can have some sort of this um, a special token for your training. So actually I explained them, but I think there is a good website about UL2. Yeah, in Google Research Brain, they have talked about it. And also they mentioned somewhere here, they said most common paradigm to build and train language model use either autorecursive decoder only architecture like Palm or GPT-3, where the model is trained to predict the next word for a given prefix phrase, or a span corruption based encoder decoder architecture like T5 or STMOE, mixture of expert, where the training objective is to recover the subset of word mask of the input. This is what exactly we talked about. On the other hand, T5-like models perform well on supervised fine-tuning, but struggle with few shot in context learning. Yeah, we discussed about that too. On the other hand, autorecursive language models are great for open-ended generation and prompt-based learning, but may perform suboptimally on fine-tuning tasks. Thus, there remain an opportunity to create effective unified framework for pre-training model. That's why they propose unifying language learning paradigm. And it said this improved the performance of language model universally across dataset and setups. UL2 framed different objective function of training language model as denoising task, where the model has to recover missing subsequence of a given input. So look, well, let's go down here. Yeah, this animation is good. So this is like R. You see that there is a token R, means uh, that is kind of noise that we have on the text. We have, for example, S-Denoiser, longest span, low corruption. We can have another X-Denoiser. They haven't differentiated between this X. They could do something like X1, X2, but you can have your own paradigm. This is like an idea that works, can be extended. Like we have sequential, so you have a token of S. So you just like helping the model to how think about to solve the problem. And you see, comparing to other paradigm like GPT, like decoder only or encoder decoder ULV2, the one-shot performance and also the superglue performance score is much higher for the ULV2. So that's the whole thing we need to know about T5, ULV2, and so on. Let's back to the paper. So one thing we forgot is the Pegasus. So ULV2 is a paradigm for training. We have another way called Pegasus in 2020, and it was another paradigm for training. I think ULV2 after it came for training encoder decoder. I think ULV2 is adapted over Pegasus, but still it's good to know that what is Pegasus. And Pegasus is like we have masked word here, and for encoder part, we're trying to predict those mask token, but we have one mask sequence, like a summary of the text, for example. And decoder part is trying to do that using that uh, language modeling objective. So you will have the combination of mask modeling and the language modeling, and these are like combined together. So that is the idea of the Pegasus. They mentioned here, let's just read the abstract very briefly. They mentioned here that recent work pre-training transformer with self-supervised objective on large text corpora has shown great success with fine-tune on downstream NLP task, including text summarization. However, pre-training objective tailored for abstractive text summarization have not been explored. Furthermore, there is a lack of systematic evaluation across diverse domains. In this work, we propose pre-training large transformer-based encoded decoder model on massive text corpora with a new self-supervised objective. In Pegasus, important sentences are removed or masked from an input document and are generated together as one output sequence from remaining sentences, similar to an extractive summary. Yeah, so we have the most important sentence here, and it has some noise also, like this mask model, and it's trying to predict that even though there are some words master. So in Pegasus, important sentences are removed. And where we evaluated our best Pegasus model on 12 downstream summarization tasks, spanning news, science stories, instruction, email patterns. Experiment demonstrated achieve a state of the art on these 12 downstream tasks. So it is mainly for like summarization. So it's somehow getting the whole idea of the text that you're giving it to the model, even though you are masking some of the tokens there. So it was like a training paradigm. And in the paper here, we talked about in Blank T5, they use Pegasus for training, for like pre-training part. So that is the whole thing. So comparing these two, because of using that heavier attention, heavier MLP and routing system, it seems like ColT5 is faster. And now let's go down. They're talking about the flops. Like if you have vanilla attention, you will have the query key and the value multiplication. So these are the number of flops we need. For attention, QKV, it was self-attention. So we have two like query and value multiplied together there. Here we will have like ND2, ND2, and we will have the feedforward layer in this number of flops. So you see that for line T5, because they have applied the localization, and as I said, there is a mean pooled summary. So it's like we have a long text, you get a windowing. I haven't read the long T5, maybe there are some details I'm missing, but overall, it's like um, localization over the long text and then applying the attention on top of that. So it's reducing number of flops. Then they talk about conditional computation. Like one way is mixture of expert. For example, mixture of expert route input through a small portion of expert submodule, bringing to bear only the parameters most relevant to the input. So like you have multiple expert. One is like great for the heavier. So actually what we are doing here is some sort of doing that using that routing system is like we have an expert for extracting the uh, objective, and we have light attention is just like helping that. So these are like expert, these are another expert. These are very similar to the mixture of expert. But here it's calling that like we can have a conditional computation and just to improve the inference time. So it said in context of retrieval augmented models, numerous work rank retrieval passage by the relevance to the query and process only the highest scoring passages. This is very similar to what is done in the ColT5. And that's why they have in ColT5, they have conditional computation. So, and they also talk about device utilization. They are mentioning flops is not only important, but also the device utilization and like memory footprint, stuff like that are very important. That's why they applied multi-query attention. And multi-query attention, we will see it in this video or next video. I don't want to take this video longer. Maybe next video when we want to implement some code for ColT5, we will see there are some library implementing multi-query attention. It's sharing head for keys and value to reduce memory bandwidth overhead. At the end, they are comparing these three, like T5, the long T5, and ColT5. And ColT5 is less computational heavy because of the routing system that we have here. So they also talk about training objective as we discussed, like long T5 use of Pegasus. They, in this paper, the ColT5 used the UL2, a mixture of span corruption, prefix, and causal language modeling. Now you know all of these together. And I think for this video, it's enough. Maybe I can start explaining routing in the next video and then start write some codes because when we are reading this, we can uh, start writing code. It's very simple. Let me maybe read through it a little. So it said ColT5 reduced the cost of processing long document through conditional computation, following the intuition that some tokens are more important, therefore benefit more than others from heavy computation. So first types of token may inherently require less computation, such as filter words and punctuation. Second, especially in line document, larger part of the input may not be relevant to the correct question, task, or processing stage. This is what we discussed. So the cold conditional computation mechanism consists of three components: routing module, conditional feedforward, and conditional attention. All tokens are processed by a standard lightweight attention and feedforward layer. Routing module additionally select important token from an input at each attention or feedforward layer. And a heavy conditional layer apply additional computation to routed token. So let's go to the routing. I think uh, the video took longer. See you in the next video. Thanks.